Okay, welcome again to our journey into complex analysis, and we're having a look in, this is section 4, where we're looking at the complex logarithm and complex powers. So we defined last time the complex logarithm and the general logarithm and the principal logarithm, and now we're going to do a similar thing for powers. So you may recall from your earlier real analysis that expressions such as 3 to the root 2 can be defined by writing 3 to the root 2 as e to the root 2 log 3. And because we know what e to the x means in the real world, then this gives meaning to 3 to the root 2. So we can use this idea from real analysis to motivate our definition in the complex plane. So I'm going to define z to the alpha to be x, the complex exponential of alpha log z, where z is not 0. So we cannot take powers of 0. Now, so this is the multi-valued logarithm, and so we can see then that this is a multi-valued logarithm. So in general, this is going to be multi-valued as well. In some cases, for example, if I put 4 to the half, well, 4 to the half better be plus or minus 2, which is only 2 values, and you can actually show that that in fact is what happens when you apply the definition. So in general, z to the alpha will be an infinite set, but there may be examples where it's only a finite set of different numbers. So we can make it single valued by simply replacing the little log with capital Log, and we talk about that as PV of z to the alpha. So that's the principal value of z to the alpha is e to the alpha log z, capital Log, z again for z not 0. So best thing to do with this is to have a look at some examples and do some calculations. So we're going to find 2 to the I, and we're going to also find I to the I, which should be interesting to see what happens when you raise I to the I. I won't show you at the moment. So we're going to start off with 2 to the I, and so 2 to the I is by definition e to the I log 2. And now we have to work out, this is the multi-valued logarithm of 2. Now the principal, the modulus of 2 is 2, so we have ln 2, plus the principal argument of 2 is 0, and then we have to add on 2k pi I. So we have then e to the I log 2 plus 2k pi I, where k is an integer. Now I'm going to simplify this a little bit. I can multiply this I in, so I squared gives me minus 1, so I get e to the minus 2k pi, multiplied by e to the I log 2, and e to the I log 2, I can use Euler's formula and write that as cos log 2 plus I sine log 2. And there it is. There is the real part, and there is the imaginary part of 2 to the I. And notice there are infinitely many values of this because k can be any integer. So 2 to the I then is a set of values. There they are. If I want the principal value of 2 to the I, then we take the principal logarithm, in which case the argument is 2. Sorry, the argument is 0, I should say, and so we put in k to be 0 in. And then I'm just going to get cos of log 2 plus I sine log 2. So there's the principal value of 2 to the I. Now if we look at I to the I, which is quite an exciting thing to do really, is, so by definition then, this is e to the I log I, and I has modulus 1, log of 1, 0, and then the principal argument of I is pi on 2, so I get so I to the I then, sorry, the log of I is I log 2 plus 2k pi, where k is an integer, and I can multiply the two i's together here, so I get e to the minus brackets pi on 2 plus 2k pi, And again, we get an infinite set of values for I to the I. If we take the principal value, however, putting k to be 0, we get e to the minus pi on 2. Now, a couple of lovely things about that is it's very nice that when you raise I to the I, look at the answer, it's a real number. So I to the I is real, and there's all our favourite constants, pi and e and so on, all connected back with I. That's a pretty formula. The principal value of I to the I is e to the minus pi on 2, which, as I mentioned, is real. Now, you perhaps thinking, well, what happens if I work out say 4 to the half, the square roots of 4? Well, you'd hope to get just 2 and minus 2. And I leave you again to go back to use the definition to actually do the calculations and convince yourself that when you work out 4 to the half using our new complex definition, when you simplify it all, you do in fact only get two values, 2 and minus 2. So the square root of 4 is 2 and minus 2. And indeed, 4 squared is still 16. It doesn't come to any other value. So you might like to check that yourself from the definition. The little final example here, I'm going to find the principal value of I to the 6 plus 2i, just as an extra example here, and I want to find PV of that. So again, you go back to the definition. This is going to be e to the 6 plus 2i capital log of I. Now the log of I, principal logarithm of I is I pi on 2. So we can just expand this out. We get 3 pi I from this times this, and then we get e to the minus pi. And so now e to the 3 pi I, of course, is just minus 1, because we go around through 3 pi. And so I just get minus e to the minus pi, which, by the way, again, happens to be a real number in this case. Well, just a little challenge problem for you to play with, to work out it's not very hard actually, to show that the real part of the principal value of minus 1 plus I squared to the I. Now be very careful here, you cannot multiply the 2 times the I. We don't know that that's valid for the principal value. It is for the general value, but not necessarily for the principal value. So at this stage you must go back to the definition, which will be e to the I times the logarithm of minus 1 plus I squared. Okay, so you're asked to show the real part of that is minus e to the pi squared times cos of log 2. Now I wanted to mention just a little bit on branch cuts, which we sort of skipped over, and I should put a little bit on that here. So the log function is not analytic, as we saw, on the negative real axis and at z is 0. So in terms of a picture, that just looks like this. That means our logarithm function is not analytic here, nor back along there. Now this ray is called a branch cut for the principal logarithm. I now want to take a real alpha between 0 and 2 pi, and I'm going to define a family of logarithms, log sub alpha, not to the base alpha, they're all to the base e. This is log sub alpha of z, and I'm going to define it in the usual way by log of mod z plus I theta, except now I'm going to have theta to belong to the set of arguments of z, but where the theta lies between alpha and alpha plus 2 pi. So we're going to then redefine this family of logarithms. So that means log of our capital log I can write now as log small log pi of z. So here we're taking alpha to be pi, that's the cut along here. So now we're taking, if you like, an angle alpha here, and redefining this new logarithm. So this function again is going to be analytic except when z is naught, by the same arguments we saw before, and also on this ray that's shown here. So this ray is called a branch cut, corresponding to alpha. And so these logarithms are going to, this new type of logarithm is going to be, it's going to have single valued, and it's going to be analytic except along this ray and at 0. And it's sometimes convenient to take a different branch of the logarithm, especially later on when we're going to be dealing with integrals where, for example, the contour we're integrating along may happen to involve logarithms, and it may happen to go along across the negative real axis, and none of our theorems will hold because we've lost analyticity. And so what we'll do is we'll move the branch cut somewhere else, over here or something, in such a way that then we have analyticity and our various theorems can be applied. We'll see a bit more on that later on.